improper integrals. Okay, cool. So let's try to remember what we were talking about over here. I guess we left these conclusions down here. So maybe we should start by filling those in. The integral that we talked about last time was specifically the function 1 over x, or the function 1 over x squared. But what we saw, and what we can sort of record down here, is that for any function f of x, if we are trying to compute a definite integral from a to infinity, which is not technically a definite integral. In fact, trying to say it that way makes it improper. Right? The trouble being that the infinity is not, technically speaking, a number, and this object is only defined when the endpoints, the bounds of integration a and b, are real numbers. We could instead define this as a definite integral. So from a to b of f of x, this is a fine integral. This is a proper integral and something that we know how to compute. And then once we've computed that, we would take a limit as b goes to infinity. Right, so this was sort of that big punchline from the video, is that in order to compute an integral that's going off to infinity, we would have to compute a definite integral sort of up to a finite point, or I guess on the right-hand side, from a up to a finite point. But then we would take a limit as that finite point just got sent off to infinity. We would end up computing a limit of integrals. We can do the exact same thing, though we didn't see it in the video. We can do the exact same thing if our integral is going in the other direction. So if it's going from a point A off towards negative infinity, sort of off in the negative direction, we can again take an integral over a finite distance from A to B. But then when the dust settles, we can take a limit as A goes to negative infinity, right? So that's, again, we're taking, at any step of the way, we're taking a definite integral, something that we know how to compute, but we're letting that right endpoint, I'm sorry, that left endpoint get further and further and further to the negative side. And so this is sort of our strategy for dealing with these infinite improper integrals. And as always, when we deal with infinity, we have to be a little careful. What we saw in the video should serve as a warning. Sometimes we'll get actual answers for these, right? Suggesting that there is a finite amount of area under this infinite stretch of curve. And sometimes we'll actually get infinity as our answer. We always have to be careful when taking these infinite limits. All right, so in what follows, we have a little bit of practice. And I wanted to give you, I think I've been leaning a little heavily into the lecture recently. I want to give you time to practice. I want to give you between 5 and 10 minutes just to try to set up and evaluate these integrals. I'll do the first one, or at least I'll begin setting up the first one alongside you, but I want you to take some time to think through the rest of these yourself. So what we have here, right, the integral, again, this is from 1 to infinity. The infinity is the problem. So we'll end up calculating an integral from 1 to b of 1 over root x dx. And then we'll take a limit as b goes to infinity. Right, so all I've done here is I've formally said that we're computing this improper integral by taking a limit of more reasonable integrals. And then our strategy for actually evaluating this is to do everything inside the brackets first. So to completely calculate the integral out, and then, and only then, take the limit. Right, so we'll keep that limiting process out front. We're going to do that in the end. But what we have in here is the integral from 1 to b of, what is that? 1 over square root of x, that's x to the negative 1/2 dx. And that just becomes what? That becomes x to the Positive 1/2, yeah, negative 1/2 plus 1. So we get x to the positive 1/2 divided by positive 1/2, aka multiplied by 2. And we're evaluating that from 1 to b. I'm going to do one more step before I actually take the limit. I'm actually going to plug in, right? So the fundamental theorem of calculus would tell us that our integral becomes the antiderivative when I plug in the bounds of integration. So I found my antiderivative. Let's plug in the b. Let's plug in the 1. And we're good to go. So this becomes the limit as b goes to infinity of 2 square root of b minus 2. Now, we can actually turn around and try to compute the limit as b goes to infinity. And to compute these infinite limits, what we often have to do is just sort of think to ourselves. I often literally like to narrate to myself, and I think to myself, as my b values get bigger and bigger and bigger, what is happening to the square root of b? Well, b is a number that's getting larger and larger and larger. That means that the square root function also gets larger and larger and larger. Square root of b gets larger at a slower rate than b, but it continues to get larger and grow without bound. And so the limit in this case is actually also infinity. In other words, we get an unbounded expression here, right? So this just keeps growing and growing. I'll just say here it grows large. Minus 2. 2 doesn't really matter. 2 is just a small constant number. And so this whole thing then continues to grow large. And so the entire limit, we might say, it diverges to infinity. Right, so what does that mean? Or I should say, what have we done here? Actually, what we were trying to compute for our function square root, 1 over square root of x, 1 over root x loosely looks like this. I'm not going to be too precise here, but it kind of looks like 1 over x. So it has a similar shape to it as the ones that we saw in the video. This is the function 1 over root x. What we've been doing is we've been taking an integral from 1 up to b. So we calculated all of this area in here. And what we saw is that for any given b value, our answer, right, the area in here was 2 root b minus 2. And so at this point, we would then proceed, letting b go to infinity. We drag that endpoint, that right endpoint, further to the right. The area grows because b is growing. And what we see is that as that right endpoint just gets further and further and further out towards infinity, the area under here, the shaded area, just gets bigger and bigger and bigger as well. So we can conclude that the total area under the improper integral is actually infinite. So there's infinite area under there. Right, so I think this example sort of illustrates not only the mechanics of what we're doing, right, save the limit for the very last thing, but also explains why we're saving the limit for the very last thing. We're figuring out a finite amount of area and then seeing what happens as we take that right endpoint and drag it to the left. Nope, drag it further to the right. Got my rights and lefts mixed up. Let's go ahead and take about 5 minutes to work through the other ones, B, C, and D, with an emphasis on trying to set it up appropriately. If you can get to this step, I'll say if you can get to this step right here, you are golden. And then through narration, we can try to figure out whether that limit actually approaches something finite or diverges to infinity. And we can talk through, some of those as we go. But at minimum, I'd say try to get up to that step for each of these problems. I'll be quiet now and let you work. All right, I want to talk through at least the first, problem B and C. I realized as I was looking at it that D is very, very similar to B. So I think they would end up looking very similar in their answers. I left out some of the initial details, so the actual calculating of the antiderivative in each of these, right? So I have this dot, dot, dot here, but I at least wanted to get it to that gold star situation. And so what we've done in each of these is we've calculated an antiderivative. This first one was negative e to the negative x, because the negative sign in the exponent had to be accounted for, right? This was a u substitution integral. And then the 1 over x to the fifth, that was just x to the negative 5. So its antiderivative was x to the negative 4 divided by negative 4. And then as we go to plug these in, right, we plug in our boundary points. Up here, it was a limit as b goes to infinity, so we're plugging in the letter b. Down here, it was a limit as a goes to negative infinity, so we're plugging in the number a, letter a. But what we end up with is an expression involving a limit in which all of our x's have been plugged in for. The only variable left is b, or a, and when we're trying to take the limit as b or a goes in their respective direction. And again, at this point, I encourage sort of a narrative view of this. I don't want you to try to quote unquote plug in infinity, right? There's potential for mischief there if you're trying to plug in infinity, because infinity is not a number and plugging it in is not technically allowed. So if we think through sort of narratively what's happening, well, as b goes to infinity, that means we're plugging in bigger and bigger and bigger b values. That means that e to the b is getting bigger and bigger and bigger. But that in turn means that 1 over e to the b is getting smaller and smaller and smaller, right? As e to the b gets really, really, really big, 1 over e to the b gets really, really, really small. And so as b goes to infinity, this piece here is going off to 0. As I'm talking out loud, I think I made a sign error here, right? I should have plugged in the b first and then subtracted what I got when I plugged in the 0. So these two pieces should be switched, but that won't actually cause a difference in the sort of calculating of the limit piece. The end result, I think, is that this should end up being positive. So our end result, end result, is that this piece just goes to 0, and what we're left with is e to the 0, aka the total area here should end up just being 1. Down here, we have a similar process, right? So down here, we're taking the limit as a goes to negative infinity. We're trying to plug stuff in here. So as a goes to negative infinity, this piece here, right? If we take numbers that are more and more and more negative, right? So think like negative 100, negative 1,000, negative 1,000,000. As we plug in numbers that are more and more and more negative, and then we take them to the 4th power, what happens to those numbers? Right? As we plug in really, really, really negative numbers and raise them to the 4th power, what's happening to those numbers? Yeah, they become positive because raising it to the 4th power makes it positive, and they're also themselves really, really big, right? Big numbers raised to the 4th power become big numbers. Big negative numbers raised to the 4th power become big positive numbers. So our denominator here is getting really, really, really big, which means that the overall fraction, 1 over a really, really big number, is itself becoming really, really small. And so what we end up with here is an expression that ends up going to 0, just like above. The infinite piece ends up going to 0. And then what we're left with is just an answer, and our answer is 1 divided by 4 times 81, whatever that actually is. right? So I think this is how I would think about these both mechanically and then also narratively as you try to figure out what the limit is in that final step. Any questions, comments, commentary about any of these examples? Anything that I can clarify? Are we feeling okay about that? All right. Okay, cool. If we're feeling okay about this, I want to pivot to, I think, the next natural question. How would we go about calculating an expression like this? Right, so an expression like the integral from infinity to negative infinity of f of x dx. So that's calculating across the entire number line. How might we go about doing that? Well, we now have this technique for how we might go about calculating something that has a definitive endpoint and goes off towards negative infinity or off towards positive infinity. And so we want to take advantage of that in this calculation. And so what we do to make sort of meaningful sense of this, to calculate over the entire number line, we're going to do it in two steps. We first break it in half, right? Infinite number line, we're just going to chop it in half at some, arbitrary point A. So here's my number line. It's going off from negative infinity to infinity. Choose your favorite number and cut it in half. Cut the number line in half at A. Then the integral up here makes sense to think about as the integral from negative infinity up to A of f of x dx plus the integral to the right, the integral from A to positive infinity of f of x dx. So we end up being able to calculate this doubly infinite integral by sort of chopping it in half at an arbitrary point, calculating this right-hand side, oh, that's the left-hand side, calculating this left-hand side as an improper integral, and then calculating this right-hand side as an improper integral as well. So we end up with this limit as, oh man, shouldn't have used the letter A. Our new favorite number is the number C. The number C. Using A just gets us all sorts of confused. Gets me all sorts of confused. New favorite number is the number C, because then we can take the limit. Notice this first piece, this infinite integral in the direction of negative infinity. That can become the limit as A goes to negative infinity as the integral from A to C of f of x dx plus, now over here, the other infinite integral, the other improper integral, that can become a limit as B goes to positive infinity of the integral from C to B. Right, so if our favorite number is C, then we take this one infinite side as the integral from A to C, and then we let A gets dragged down towards negative infinity, and then, sort of simultaneously, we're considering the integral from C to B, so we're considering this piece, and then we let B get dragged towards positive infinity. And that's how we can sort of make meaning out of this doubly infinite f. So I think there's a good question to be asked here. And the question is, like, is this dumb? Did we just make this harder on ourselves than we needed to, right? So why, or could we have taken the integral, let's say the limit as, running out of letters here, limit as d goes to infinity of the integral from negative d to d of f of x dx, right? So here I split it at some point c, and I created two different improper integrals. Up here, I seem to be just creating one improper integral, and let a single value d represent both of the endpoints. So I have the second item pool question, just as a gut call. Is there a difference between these two expressions? Take a moment to sort of think about that. Is there a difference between the expression limit as a goes to infinity of negative a to a f of x dx versus the expression that we wrote down here, sort of splitting it and taking the two separately versus sort of absorbing both sides at the same time? I do want to give you a little bit of time to think about this, but at the same time, it will mostly just be a gut call. We'll talk about it here in just a second. Go ahead and make a gut call. I love it. I love it so much. Okay, yeah. It seems like we're split in our answers because there's two answers. I know we're split down the middle here. Go ahead and finish and reveal. So it turns out the answer is there is a difference, but that seems really unintuitive, especially, you know, to me at first glance. I thought that was ridiculous. There shouldn't be a difference. Let's talk about the difference. Let's try to zoom over here, talk about the difference over here in this white space. So I'm going to create a function. I got to think for a second. I'm going to create a function to try to understand the difference. Okay, I'm not going to think that hard. The function that I'm going to create, function that we all know and love, let's think about the function f of x equals x cubed. Okay. The function f of x equals x cubed looks like this. Right, I'm going to draw it. Oof. I was going to say I'm not going to draw it great, but that was bad even by my standards. Let's try again. X cubed looks loosely like this. Okay, that's bad, but that's good enough. X cubed looks like this. What happens if we try to compute our integral in these two different ways? First, let's try this way. So the limit as d goes to infinity of the expression integral from negative d to d f of x dx. Okay. So for any given d, let's say this is d and this is negative d, what is this integral equal to? Right? What is the integral for a specific value d of the integral from negative d to d of f of x dx? Take a moment to think about that. What would that integral be? All right, just so we have a little bit of conversation this class, turn to your nearest neighbor, check in with them. What do you think this integral should be? What should this integral be in this case? Yeah, so I heard some answers out there. I think this integral would be 0, right? The integral would be 0 in part. I mean, let's think about it. We could explicitly compute it using the fundamental theorem of calculus, but from an area perspective, right? Thinking about it in terms of area, the definite integral represents signed area. This side here is negative. This side here is positive. The function x cubed is so nice and symmetric, and that's why we love it so much. And what we see here is that the negative area cancels out perfectly with the positive area, giving us 0. So for any given value of d, this becomes 0, and we get the limit as d goes to infinity of 0. Cool. And the limit as d goes to infinity of the constant 0 is just the constant 0. Now, let's do the exact same thing, but using our other approach. So what about if we take the limit as a goes to negative infinity of f of x dx? No, what am I saying? The limit as a goes to negative infinity of the integral from a to 0 of f of x dx plus the equivalent expression involving the positive side. So limit as b goes to infinity, integral from 0 to b of f of x dx. What happens here? Well, we have to compute these separately. And no matter which one we start with, let's say we start with the positive one, I'm just computing this expression here, right? And so that's going to be, I guess, by the FTC, right? The integral of x cubed is x to the 4th over 4. So this is going to become 1/4 b to the 4th minus 0. And so we end up getting that integral is that, and then we're taking the limit as b goes to infinity. This piece diverges to infinity. While at the same time, this other piece, sort of draw it in green, right, is measuring this area. And that area is going to be limit as a goes to negative infinity of 1/4 negative 1/4 a to the 4th. And so that ends up giving us negative infinity as our answer, right? So that diverges, let me scroll down. That diverges to negative infinity. And so notice I'm being careful by throwing in the word diverges here. Both of these limits diverge. Neither of these limits is technically consolidating at a number. What that means is we end up with this expression where each of these have diverged, and we're forced to conclude that the entire thing diverges. What we don't conclude, the entire thing diverges, what we don't conclude is that this equals infinity minus infinity, right? Infinity minus infinity is a real thorny expression, right? It's one of those indeterminate expressions from Calc1. And in particular, infinity minus infinity does not equal 0. So that's sort of a word of warning. For this problem, we don't want to get infinity and negative infinity and conclude that infinity minus infinity equals 0. Instead, we just want to conclude that the entire thing diverges. Cool. So in fact, when we have these doubly infinite improper integrals, we have to split it into its two respective halves. We have to take the one half and the other half separately. And if either one of them, it turns out, if either one of them is something infinite, we just say that the entire thing diverges. So yeah, I really love that question. Again, this is sort of a concept heavy class. I really love that question because it seems like at first glance they should be exactly the same. And so it's only sort of some example like this where there's some sort of subtle difference that we begin to pick up on. Any questions about any of this? Any questions about the example that we just talked through? All right, good times, good times. Let's see, with about 15 minutes left, we got to change gears and talk about a different kind of improper integral, a much subtler kind of improper integral, an integral with an unbounded integrand, right? So the thing that we're integrating becomes unbounded. So let's start by way of example. Take a moment to try to calculate the integral that we see here in problem 9. Yeah, take 60 seconds to give that a try. All right, so your mileage may vary, but as you've been calculating this, if you're just sort of blindly plugging and chugging with the fundamental theorem, it's easy to accidentally think, oh, the variable's in the denominator, this has to be a logarithm as the antiderivative. But it's not ln, right? So the antiderivative, we'd first rewrite this as 2r to the -3. And then when we integrate, this becomes 2r to the -2 divided by -2. So we rewrote, then we found an antiderivative. We go to plug in, and we end up getting this expression, -3 to the -2 plus 0 to the -2. And if we're not careful, we'll just submit that as is and be happy with ourselves and be done with it. The trouble is 0 to the -2, that's weird. That's not a well-defined expression. What is that? Well, remember, this becomes negative. So negative r to the -2 is really -1 over r squared, right? So this is just sort of rewriting the expression above it. So this would become -1 over 3 squared minus -1 over 0 squared. And that makes it really clear that something bad has happened here, right? So 0 to the -2, not a well-defined expression because it's trying to become 1 over 0 squared, and that is just no good at all. So I guess what broke down here, right? What is the problem? Again, it comes from the theory of the fundamental theorem of calculus and the fact that we just tried to compute an integral that didn't work, right? The integral didn't work. And I want to sort of briefly talk about why. The function 2 divided by r cubed has a problem at r equals 0, right? That denominator would be 0. The function is undefined there. If we want to get fancy and graph it, right, as we often do, 2 divided by r cubed, the function 2 over r cubed, looks like this. It looks similar to the 1 over x issue, right? Or it looks similar to the function 1 over x. So our function looks like this. And if we're trying to compute the integral from 0 to 3, we actually have a problem point at 0. The function is undefined there, and our area has the potential to grow without bound, not off to infinity, right? We've seen these examples where it grows off to infinity over here, but instead, it's possible that we have infinite area as virtue of this vertical asymptote here. So this is a potential problem area here. More to the point, or I should say, right alongside the point, a definite integral, again, is only defined for 2 explicit values, right, from a to b of our function f of x. And typically, we need our function to be defined along that entire interval. So if we're taking a definite integral from a to b of our function, and our function's not defined at b, we have a real problem. And this is a second example of what we might call an improper integral. It's a lot subtler because there's not an infinity there sort of smacking you in the face, but it's still a potential problem and it's still an improper integral. So what are we going to do about it? We have to play the same game that we did before. We cannot calculate definite integrals with bounds of integration that are bad, right? Infinity was bad, and we danced around it by taking a limit of integrals that were good. And we're going to play the same game here. So instead of, I'll use the same picture. I can get back up there. Instead of taking the integral all the way from 0 to 3, as we've done here, we can instead take an integral from a to 3, right? So instead of taking that improper integral, we can take this integral, which is well defined, right? Our function is defined all the way from a to 3, no problem at all. So we're totally allowed to calculate an integral from a to 3 of 2 over r cubed dr. And then we're going to take that number a and inch it closer and closer and closer to the number 0. So we'll take a limit as a goes to 0 from the right-hand side of that expression there. Right? Maybe I think to explicitly answer the question 10 as it's written, we can estimate the integral by taking a limit, by taking a integral from a to 3, and then we can improve that estimate by inching that that left endpoint a little bit closer and closer and closer to the number 0. And so in this limit process here, that is actually what we get. I think just like in the video, I should really have this down here. Comment. So just as before, we're using this limit idea to dance around the improperness of this integral. And now we can actually compute an answer that makes sense. And as we might expect, it turns out that this 1 over 0 squared was a major problem, indicating a major issue from up above. So let's actually calculate this now. So in trying to calculate the integral from 0 to 3 of 2 over r cubed, try that again, 2 over r cubed dr, we would need to calculate the limit as a goes to 0 from the right-hand side of the integral that's actually computable now, the integral from a to 3 of 2 over r cubed dr. All right, and now this just becomes a problem, you know, similar to others that we've done. We have to be a little careful. I'm going to keep the limit out front, and we'll deal with that at the very end. We have the integral, let's see, that integral, just as above, the integral becomes negative 2 r to the, that becomes 2 r to the negative 2 divided by negative 2, evaluated at a and at 3. And that just becomes the limit as a goes to 0 from the right of negative 1 over r squared, evaluated at a and evaluated at 3. So what I'm going to do is I'm going to plug in those bounds of integration, and then I'm actually going to try to compute this limit. The limit as a goes to 0 from the right. Let's see if we can get this right, -1/3 squared, so that's -1/9 minus a -1/a squared. Let's be really clear. This first one is a 9. That's a 9, a long tail. -1/9 plus 1/a squared. Limit as a goes to 0 from the right. Okay, so now we're at the equivalent moment. This is what I called like sort of the gold star moment from above. If we've gotten here, we're so happy. Now let's compute the limit. And to compute the limit, again, I want to take a narrative form here. Let's think out loud. As a goes to 0 from the right-hand side, it is a positive number that is getting smaller and smaller and smaller, closer to 0. That small number, when we square it, what happens? It stays positive, and it gets even smaller, right? If you square a fraction, right? 1/2 squared is a fourth. 1/10 squared is 1/100th. If you square a tiny decimal, you just get an even smaller decimal. So that a squared is itself going to 0. That means that this denominator is getting super, super, super small, which means that the overall fraction is getting super, super, super big, right? 1 divided by a teeny tiny number is a huge number. So as a goes to 0 from the right, this piece right here as a whole is getting really big. And so the limit, we would say, diverges. This whole thing diverges to infinity. Right? -1/9 plus a huge number just continues to stay huge. So the process, similar to before. The issue, of course, is that now we have to be very careful about where our improper points are coming from. It can be hard to find them. Here we had to know a little bit about what the function 2/r³ looked like to recognize that 0 was a problem point. Okay, we have about 3 minutes left, maybe a little less than 3 minutes left. I want to end on problem 13 because there's something kind of subtle here. Because we don't have that much time, I unfortunately might rush this just a little bit faster than I would otherwise, but that's okay. If you don't want to write this down and just momentarily follow along, that is a-okay as well. I'm going to very quickly compute this integral. We will use the same steps that we did up above, which means that I'm going to recognize that at 0, there's a problem point, right? I'd end up with a 0 in the denominator of the thing that I'm integrating. So I really want to compute the limit as a goes to 0 from the right of the integral from a to 3 of, this time it's 2 divided by the square root of r. So just like before, 2 divided by root r, that becomes 2r to the -1/2. The antiderivative of that is 2r to the +1/2 divided by +1/2. So that's going to become 4r to the +1/2. So 4 square root of r. We're taking the limit as a goes to 0. The antiderivative was 4 square root of r, and we're plugging in a and 3. We get to our gold star moment, limit as a goes to 0 from the right of 4 times the square root of 3 minus 4 times the square root of a. And after this gold star moment, what we see is that as we plug in numbers that get closer and closer to 0, 4 times the square root of a gets closer and closer to 0. And so this whole thing actually converges to a finite number. It converges to 4 square root of 3. And that is, in fact, our answer here. We get a finite amount of area here. Now, why did I include this as the final example? There's a warning here, and I want to issue the warning before I let you go. The warning is this. If I had proceeded as, in sort of like a blind manner without noticing the improper integral, if I was just taking the integral from 0 to 3 of 2 over root r dr, and as a result, I got 4 root r evaluated at 0 and 3. So this would just be fundamental theorem of calculus style. I would get the exact same answer. This would become 4 root 3 minus 4 root 0, which is just 4 root 3. I would get the same answer, and yet this process is technically incorrect. We get the right answer and we do a lot of the same mechanics, but notice at a conceptual level, the object that we're talking about here, and specifically the step that we made going from here to here, is not okay. We were using the fundamental theorem of calculus to find an antiderivative and plug in the two endpoints. And the fundamental theorem of calculus as a theorem doesn't apply if our function is undefined at one of the endpoints. So there's this interesting issue here where we get the right answer and it feels like there's very little difference between what we did all over here and what we did over here, right? They feel very similar. But by introducing this limit, we make sure that we're standing on strong conceptual ground, and we make sure that we are actually allowed to compute this antiderivative. Okay, and that took me 1 minute over. Thank you so much for being patient. As always, I'll try to dismiss you by rows. First row, as you are ready, you can head out. Thank you all so much. Have a great rest of your day.